Okay, so Hibernate started out uh, around now 14 years back in 2001 by a person called Gavin King. So at that time, EJB and EJB version 2 specifically was what was the most important technology uh, that was solving business problems through Java platform. So there was with EJB2 there was a very increased a largely increased set of complexities that a developer had to face. With EJB2 you had to have 4 sets of interfaces, and then the specs they were very intrusive, specifications they were very intrusive, and they needed to be your whole code needed to follow a very strict set of specifications, and a lot of implementation of interfaces and guidelines that needed to be there in configuration for EJV2s to work for your business solution. So from the RDBMS side, it was thought that there needs to be a solution that's independent and non-intrusive, as in it should not intrude into your business code, and it should also solve the RDBMS independence problem. So Hibernate was conceptualized. It provided support for mapping. It provided support for diverse vendors, one abstraction. It provided support for a unified language that dealt with all kinds of databases. So it was something essentially there to keep business logic unaware of the RDBMS side, essentially demarcating the layer, RDBMS persistence layer, from your business logic. Any questions out there? All right, moving on. Okay, so it's just showing you that Hibernate can talk to Oracle, MySQL, and Derby, which is also a database solution completely implemented in Java. So it's talking about vendor independence. There's just one user interface and one Hibernate instance that can talk to all kinds of databases for you. All right, so going into the basics of RDBMS. So we all know data are a set of facts, and information can be derived from those set of facts, and to be available as an input to that information logic, data has to be structured and formatted in a certain way, so calculations and statistical analysis can be performed on it. And okay, it's saying what a database is. So a database it's actually formally providing you a way to store data in a very standard, consistent, and optimal way. So if you, I'm sure you all have worked on databases, Oracle, MySQL. It gives you a standard way in which all data can be updated, retrieved, analyzed, and there is a consistency, as in it's all standard databases. They follow a certain SQL language standard. There are some low-level differences in how all of that is implemented, executed, and there are differences in how certain sets or certain arcane parts of SQL are supported by various database systems, but by and large they all support SQL as it exists in a standard way. So a database essentially gives you that unified interface uh, to query your data, update it, maintain it, and then a database also lets you build a role-based access to that data. So you can have a set of users who are able to administer that data, a set of users who can only query it. So that access security hierarchy can also be implemented by a database. And so those pretty much are the services that a database provides for you. Moving on. Yeah, so this is again, database constraints are something that RDBMS users constantly have or constantly utilize for structuring that data and constraining its values and structuring it according to how they would need to query it, how they would need to view it. There are a bunch of constraints, like not null constraint is something that you so if you have a database, if you have data in which you have first name and last name, then an obvious constraint on the last name is that it cannot be null. And then let's say you also have SSN, then an obvious constraint is that each SSN is going to be unique for each individual. And then primary key is an RDBMS concept. I mean, anyone who's used databases knows about it. It's something that we use to provide a unique entity to your tuple, which is actually a row in your table. And foreign key is how we maintain references between one relation to the other or one table to the other. And then you can have checks that a column value needs to be of a certain type, and then you can provide default a default value to your column in case there is no value provided in your SQL. So these are some very basic SQL constructs. I see a question. Hang on one moment, sorry. What database normalization is, essentially normalization is done to optimize the structure of your databases, of your data as it's structured in your relations or tables. So if you are at a certain normal level in your data structure, in the way you structure your data, then what you'll find is that it's easier and consistent to query that data, and it's easier to update that data as well, and it's also easy to view that data as it's so in this slide you see that the employee and the department tables are normal, so it's very easy to create this diagram. But if, let's say, employee and department, both the employee and department tables were together and not normalized, then it will be a little difficult to view the entire structure as it's actually existing, because having redundant data in your employee plus department table would mean that one department would keep getting repeated for employees who are of the same department, which is not normal. So it's easy for you to view it as well. It's easy to query it if you are at a certain normal state in the way you formatted your data. So there are various levels of normalization. So you have, let's say you have information, your employee information, their dependent information, and the manager information with you, and it's not structured in the way that this diagram shows you. Then the first thing you need to do is to be at first normal level. You collect your employees and your department values in a separate table, so that there is no repeating field. So if that was not there, for each employee, if he belongs to the same department as the previous one, department data would be repeated. So that will be your first normal form. The second one is talking about having a unique field present as an employee ID department code, which identifies your entire set of rows in your table or in your relation. So if you have one employee ID and it's different than the other one, then there is no ambiguity in terms of who those the two records are different, even if all the other fields are same. So let's say there's one individual, sorry, yeah, so as I said, so let's say if there's one individual uh, who's got the same name as the other one and is working in the same department, then if there's no unique key out there, then it's very difficult to differentiate the person from the other one. So if you are at your second normal form and have a unique key like employee ID, then it ensures that there's no ambiguity even if all the other fields are same. The third normal form, which is usually not implemented these days because memory is memory is not a constraint, so you can have redundant data, but performance is a constraint. So at the cost of performance, at the cost of memory, you increase performance, something that I'm going to talk about later. But third normal form is that none of the keys or none of the attributes or columns should depend on anything else than the primary data. So I can go in depth and give you an example, but at this point and in future modules, we will not be using third normal form. So it's something you can read about if you go into normalization in depth. Okay, and the last point is that yeah, so normalization, I think it's been brought up from old RDBMS days. Online transaction processing. If your data is formally at second normal form, then it will be most optimum for real-time online transaction processing. So any questions out there? Okay, moving on. Okay, this is also talking about what a database system is. So a database is a group of related data ability to have a security access around it. So at this point we're talking about persistence of data, which is where databases actually come in, which is what their core role is. That is, data needs to be persisted. By persisted, what we mean here is that it needs to survive application outage. It needs to survive database. Even if your database is brought down, it needs to survive. So essentially, it needs to be there either on your hard disk memory or on tape, or stored at a physical location to be called as persisted data. because it needs to survive the outage of the system. And a database is used to have this persistence service available to you. Moving on. So we've all worked with SQL, structured query language. It's actually an interface that databases provide for you to manage the data that you're going to store in your database. And at a high level, there are two flavors of the kind of SQL that you're going to be dealing with. One is data definition and the other is for data manipulation. So data definition essentially is saying how your data is going to be formatted, as in what are going to be your relations, what's going to be your schema. By schema I mean how does what attributes or what columns reside in what table, and how are they going to be referencing each other, and what are the types of each columns. So to be able to create that, manipulate that, there is a set of instructions that are provided by SQL, and they fall under data definition language. And parallelly, there's something called data manipulation language. So data manipulation deals with the actual data that resides in your schema, as in the values of those columns and how they can be updated, how they are retrieved and viewed. So the set of instructions to do those things fall under data manipulation. So we've all seen SQL is actually very English-like, as in when you say select, it's actually in English it's saying that you're supposed to select something from somewhere having this constraint, so where these things are true. So it's very English-like. So it was actually started as a structured English language by these folks, Donald D. Chamberlain and Raymond F. Boyce, and it was called SQL, which is structured English language, and then it came about as SQL, a standard interface for all of us to use. So an important fact out here is that each database vendor, Oracle or Microsoft SQL or MySQL for that matter, they have their own dialect of SQL. There are slight differences. So all basic functions perform the same way, but all arcane functions like let's say how you are partitioning your tables to view your data, or how your max counts are getting calculated. Those are some things that are different between databases, slight differences. So those differences are something that are implementation specific, and they are dialects that each vendor provides. Any questions out there? Okay, moving on. Yeah, so these are the basic instructions that fall under DDL and DML specific set. So as you see, DML is talking all about data and all about how we query that data, how we delete or update that data. Meanwhile, DDL is talking about creation of or alteration or dropping of objects, as in more specifically tables or views or yeah. So these are the basic instructions that that SQL provides as data definition and data manipulation facilities. Moving on. So as I said, apart from just data, a database also lets you secure that data. So there are two other sections of SQL: data control and transaction control. So data control is actually there to help you manage your users and the privileges that users have. So there are situations where you don't want users to actually have the ability to delete tables, or you don't want the users to even have the ability to update a table, just have users read them. You can have that implementation using data control languages. So you're essentially what you're doing is either granting users privilege or revoking privileges. So there are just two commands that you can use to do that: grant and revoke. So transaction is something that we will be talking about heavily in the coming modules. A transaction is something that is actually a very basic business interaction, a very a constrained business interaction that encompasses update of one or more than one tables, or read or write of more than one sets of data that has to be done completely. So what I'm actually saying here is that, let's say if you need to let's say you have to withdraw money from an account which is being maintained at the background in a table called accounts. So your transaction is going to be withdrawing. Your transaction is actually going to be updating of a row in that table and creating another entry in your transactions table which shows that you've actually done the withdrawal. So this would be an entire transaction. So if you just end up updating one row in that account table and not making an entry in your transaction table, it will not leave things consistent. So you've actually done the transaction, but you've not made an entry for that transaction. So your business interaction is going to be a combination of these two entries, which is going to be a complete transaction. So a transaction has to ensure that whatever is comprising of a transaction has to complete for it to be successful. So let's say if you are unable to update the transaction entry in your transaction table, you will need to withdraw, you will need to roll back, which is the technical term, actually not make that update that you made previously in your account table. So what we're talking about is either you completely do both the entries, that is the update entry in your account table and making an entry in your transaction table, or you do neither, so for your data to stay consistent. It's something that we call atomic, as in either it happens or it doesn't. It's one complete set of consistent operations through SQL interface, SQL instructions, and the way to do that is using the transaction control statements like commit, or having a save point, which is Oracle specific way to demarcate what a transaction set of transaction statements are, or rollback, which is a way to say that your transaction cannot be completed and whatever's already been done needs to be rolled back. And set transaction is a way to define isolation level.